Namaste. Welcome back to Murali's World of Physics. In this video, which forms the second part of the video on the physics of music, I'll be discussing some more aspects of the application of physics in music. In the first video, I had mentioned that the human voice box, that is the larynx, is the most remarkable source of sound. The voice boxes of animals, birds and other living things, although they are more or less similar to that of the human voice box, the finer details differ. And also, these other voice boxes are not as versatile as the human larynx. As I had already mentioned before, sound is produced by vibrating objects which in general execute simple harmonic motion about some equilibrium point. These sound sources can be broadly categorized into two types, namely natural sources and artificial or man-made sources. Natural sources of sound include springs and rivers, waterfalls, sea, wind, rain and thunder, voice boxes of humans, animals, birds and other creatures, etc. To the artificial category of sound sources belong automobiles, airplanes, helicopters, trains, explosions, factories and industrial motors and other machines, air conditioners, home appliances such as vacuum cleaners, fans, mixer grinders, etc. And of course, the various musical instruments that are part of our detailed discussion today.
The sound vibrations from a given source travel outwards in all directions in the form of sound waves from the sound source. As illustrated here, this is the sound source which vibrates and produces the sound. So this sound then travels into the medium around the source in the form of sound waves. It was already mentioned that sound is a form of mechanical energy produced by vibrations. Thus, we need particles in the intervening medium for transmitting these vibrations. Hence, sound cannot be propagated through vacuum. Now, this is illustrated via what is known as a bell jar experiment. In this experiment, we have a bell jar which is connected to a vacuum pump, and therefore this can be evacuated. So inside this we have an electric bell which is given electrical connections to an outside source of electrical current. Now the electric bell is connected, so we hear the sound of the bell outside. Then gradually the air inside is removed by the vacuum pump. It is observed that the sound of the bell gradually decreases until finally it fades out completely. So this experiment proves that sound cannot propagate through vacuum. That means a sound requires a medium to propagate. Of course, the medium can be either a solid, liquid or a gas. Of course, the most common medium through which sound is transmitted is air. That means just like electromagnetic radiations, sound is transmitted through different media in the form of waves.
The propagation of sound waves along a medium can be very easily demonstrated by means of a toy telephone, with which I am sure many children will be familiar. Its main parts are a certain length of cotton thread stretched between the bottom faces of two plastic cans. Children sometimes use the inner parts of matchboxes in place of these plastic cans. So these the two ends of the string are fixed to the bottom faces of the two cans. One of these will act as a mouthpiece into which somebody speaks, and the other can act as an earpiece, and the ear of the person listening will be held near this second can. the string has to be, of course, stretched under tension. Well, details about the stretched string and the stretched membrane will be discussed later on. So the bottom face, which acts as a stretched membrane, is excited via the sound waves from the speaker's mouth, and these are transmitted through the string to the stretched membrane of the earpiece, and from here they are transmitted through air to the receiver's ears. That is how the sound waves are transmitted through various media from the source to the receiver. Look at the two kids enjoying with their toy telephone.
Hello. Hello.
In general, the waveform need not be sinusoidal. It can also be of any shape as illustrated here. This shape can be anything, but only thing, this shape is repeated at regular intervals of time. A wave is any general pattern traveling along one direction with a given speed. So this is traveling along the x direction. Now in the wave there will be some quantity that is being propagated. This can be a position of the particle or some other physical quantity which propagates as the wave. It is usually found that such quantities which are propagated as waves can be described mathematically in terms of a partial differential equation, something similar to this. Dou square f by dou t square is equal to v square dou square f by dou x square, where f is the quantity being propagated, t is the time, and x is the direction along which the wave is being propagated, and of course v is the speed with which the wave is propagated. It can be seen that the most general solution to this differential equation is of the form f is equal to some function phi of x minus vt plus the same function. Now this is a function of x plus vt. So notice the difference, x minus vt and x plus vt. This is seen to be a superposition of two solutions, phi of x minus vt and phi of x plus vt. So the first one, phi of x minus vt, represents a wave which is traveling along the positive x direction. So not the negative sign here. So this is a wave traveling along the positive x direction, whereas the solution with a positive sign here represents a wave which is traveling along the negative x direction. The speeds of both solutions are identical, equal to v. In a particular case, the actual wave may be either of these or a linear combination of both of them. The most common wave is of course the sinusoidal form, and the mathematical representation of such waves is y is equal to a sin kx minus omega t, where the omega has the same relevance as we have seen earlier. It is the angular frequency, and the actual frequency with respect to time is given by f is equal to omega by 2 pi, and the new quantity k is called the wave number or wave vector. If we take a snapshot of the sine wave at a particular instant of time t, then it will have a form which is represented by means of this diagram. So y is the quantity that is being propagated in the form of waves, then x is the direction in which the wave is propagated. So here the quantity that is represented here, that is lambda, is called the wavelength. What is the wavelength? It is the distance between two nearest points having the same phase along the wave. So for example, if we consider a point here, then traveling along this direction we get a complete wave like this. So that distance represents the wavelength. Now here we see that there is a positive maximum and a negative maximum. The positive maxima are called crest and the negative maxima are called troughs. So the wavelength can be defined as the distance between adjacent crests or between adjacent troughs, or between any 2 points at which y is equal to 0. So y is equal to a sin kx minus omega t. Let x1 and x2 be two nearest crests. Then lambda is equal to x2 minus x1 by definition. The amplitudes at these points must be the same at the same instant of time t. So therefore sin kx2 is equal to sin kx1, or lambda is equal to 2 pi by k. Or inverting this, we have k is equal to 2 pi by lambda. So therefore k is the number of waves in a distance 2 pi. Now this k by 2 pi can be viewed as the spatial frequency, just like f is the time frequency. The number of waves per unit distance along the direction of travel of the wave, it is also called the wave number, that means nu bar. This is expressed in terms of centimeter inverse 1 or meter inverse 1. A vector k in the direction of travel of the wave having a magnitude equal to k can be called the wave vector. Omega is the angular frequency, that is equal to 2 pi f, where f is the frequency. The wave travels a distance equal to one wavelength in a time equal to one period of the wave. That means the period t is equal to 1 by f. Therefore the speed v can be calculated as the distance travelled divided by the time taken. So lambda by t, that is f lambda. But of course f is equal to omega by 2 pi, therefore v is equal to omega by k, or omega is equal to v into k. Now this particular relation is very important. It is known as the dispersion relation. Of course, this is the simplest form of the dispersion relation. In most common materials, v, the speed of the waves, is independent of k. Such media can be called non-dispersive. Whereas in certain other media, v depends on k. The velocity will depend on the wave vector. They are called dispersive media. In such media, the waves of different frequencies are found to travel with different speeds, and the sound may get distorted as the wave travels forward.
Basically, there are two main types of sound waves depending on the direction of the vibrations of the particles involved. The first type is the longitudinal waves, where the motion of the particles will be parallel to the propagation direction. The second type is the transverse waves, where the motion of the particles involved will be normal to the direction of propagation. The longitudinal waves are also called pressure waves. These consist of alternate compressions and rarefactions. This occurs in solids, liquids and gases. So in the compressions, the particles are closer together as compared to the regions of rarefactions, where they are further apart. And the motion of the particles will be, the vibration will be like this. So that is along the direction of the traversal of the wave, which is like this. On the other hand, transverse waves are those where the motion of the particles will be normal to the direction of propagation. This is the direction of propagation, and the particles will be vibrating in the vertical direction. And we have alternate crests and troughs, which correspond to the maximum amplitudes of vibration in either direction. These transverse waves are also called shear waves, and these are possible only in solids. They result from shear stresses associated with shear strain. In order to support transverse waves, the medium should possess rigidity. In fact, that is the reason why that is possible only in solids, because fluids in general do not support transverse waves because they don't possess the sufficient rigidity. So since fluids cannot resist shear forces, propagation of transverse waves inside the bulk of fluids, namely gases or liquids, is not possible. However, it should be understood that the waves on the water surface are transverse in nature. This is most easily illustrated by floating leaves on the water surface, which go up and down at the same place when the waves are produced. It is actually the surface tension of the liquid which makes this possible. In fact, if you remember, in my earlier videos I had mentioned this, the surface of any liquid acts like a stretched membrane. The speed of transverse waves in a bulk solid, that is transverse waves, is given by square root of S by rho, where rho is the density of the material and S is the shear modulus of the material. For longitudinal waves, the velocity is VL is equal to square root of Y by rho, where Y is the Young's modulus of elasticity and rho is the density. The velocity of sound in case of extended solid will be VL is equal to square root of B plus 4 eta by 3 divided by rho, where B is the bulk modulus and eta is the modulus of rigidity. So in fact these are different. For a longitudinal waves in a gas, the velocity is given by square root of P by rho, where P is the pressure of the gas. For a liquid, P has to be replaced by the bulk modulus B. As already mentioned, the general solution to the wave equation is a superposition of the waves of the forms phi of x minus Vt and phi of x plus Vt. Now these are called travelling waves. Since these waves are mechanical in nature, they carry energy with them through the medium. The direction of energy transport will be the same as the direction of propagation of the wave itself. Of course, the most general solution is of the form A times phi of x minus Vt plus B times phi of x plus Vt, where A and B are constants. This is the general principle of superposition and is valid in several areas of physics. For example, electromagnetic waves, wave function of quantum mechanical systems, etc. Now, phi of x minus Vt is actually a forward traveling wave, and phi of x plus Vt is a traveling wave in the backward direction. That means this is in the positive x direction and this is in the negative x direction. In the case of sine waves, these are respectively represented by a sin kx minus omega t and a sin kx plus omega t, as we have already seen earlier. Now consider two traveling sine waves of the same frequency and amplitude traveling in opposite directions, one in the positive x direction and in the other in the negative x direction. The resultant amplitude at a given point is then given by a linear superposition of these two. That means y of xt is equal to a sin kx plus omega t plus a sin kx minus omega t. After some mathematical manipulations, this can be reduced to the form 2a cos omega t sin kx. And this particular resultant wave can be seen to be not of the form of the traveling waves, either of these two traveling waves. It is in fact called a standing wave. It has the same frequency as the two individual traveling waves, but the amplitude is twice the individual waves. Also, there is no net transport of energy. Now in this animation, we see the formation of the standing waves as a result of the superposition of two traveling waves, one in the forward direction and the other in the opposite direction.
At this point, we have to discuss a very important physical process called resonance. A physical phenomenon of much importance in any discussion of sound, music and musical instruments. The phenomenon of resonance is also relevant in many other fields of physics such as atomic and molecular physics, nuclear physics, electricity and magnetism, etc. Any vibrating system has a set of characteristic frequencies. These are called natural frequencies. The lowest of these frequencies is called fundamental frequency, whereas the higher frequencies are referred to as overtones or harmonics. There is a difference between overtones and harmonics. Harmonics have frequencies which are necessarily integral multiples of the fundamental frequency. Such a restriction is not there as far as the overtones are concerned. A system can be set into vibrations by an external driving force or agency at a given frequency. Such vibrations are called forced vibrations. On the other hand, left to itself, in the absence of any external influences or driving forces, the system will have the natural tendency to vibrate at one of its natural frequencies, and this is called natural or free vibrations. It is seen that the amplitude of vibrations will be maximum when the driving frequency matches one of the natural frequencies of the driven system. This is the phenomenon of resonance. If we vary the driving frequency over a range covering the natural frequency of the driven system F0, then we obtain what is called the resonance curve. This is nothing but the plot of the amplitude of vibrations as a function of the driving frequency. As we vary the frequency from lower values to higher values, the amplitude gradually increases, reaches a maximum at F0 and then decreases on the higher frequency side. The rate of fall on either side of F0 will depend on the various characteristics of the system, or in other words, the width of this resonance curve will depend on the characteristics of the driven system. The phenomenon of resonance can be demonstrated in various ways, and one of the simplest methods is what is known as the resonance coulomb method. Here the setup consists of a long plastic tube dipped inside a glass trough containing water. So at any position of this glass tube, there is a air column inside it just above the water surface. Now we can vary the length of this resonance, the air column, by raising or lowering of the tube, or also by raising or lowering of the glass trough. We have a vibrating tuning fork which is cut just above the top of the plastic tube. So this will set the air inside the plastic tube into vibrations, into forced vibrations. We can listen to the sound, and as we gradually increase the length of the air column, we can see that the amplitude increases, becomes a maximum, and then for larger values of the length of the air column, the amplitude decreases. So this corresponds to air resonance. Also, if we keep the air column length fixed and then vary the frequency of the exciting source, we will get a similar resonance curve. The tuning fork itself can be used to demonstrate the process of resonance. In this, the tuning fork will be made of iron, and it will be excited by an electromagnet which is energized by a variable frequency alternating current source. So here we have the electromagnet, which is a iron core, or which we have a coil of wire, and through this alternating current is passed. As the current varies, the magnetic field which influences the tuning fork will vary in a sinusoidal fashion. Also, the frequency of the exciting source is variable. When the exciting frequency coincides with the natural frequency of the tuning fork, it will vibrate in resonance with the maximum amplitude. In the resonance column method, the waves from the tuning fork are transmitted downward as forward traveling waves through the air column. When they reach the water surface, they get reflected and they proceed upwards as traveling waves in the opposite direction. The two sets of waves actually interfere in the air column. When the resonance condition is satisfied, we get standing waves. In fact, standing waves are always associated with resonance. The open end of the system will be an antinode with the maximum amplitude of vibration, and the closed end will be a node which corresponds to no vibration at all. A very good example of a musical instrument with resonance column, air column, closed at one end and open at the other end, is the familiar trumpet. So it will be open at one end and closed at the end, which is closed actually by the player's lips and the reed. So the closed end will correspond to a node and the open end will correspond to an antinode. Resonance columns can also be of other two types. The second one is the air column, which is open at both ends. A very good example is the familiar flute. So we have the two ends of the flute which are open. Now actually when the flute is played, we close one or more of these holes. But even then, this hole is open, here it is open, and the hole where the last finger closes it, that becomes the other open end. Now in this figure are shown the fundamental and the three lowest overtones for a tube closed at the bottom end. All have the maximum air displacement, that means antinode, at the top and none at the bottom closed end. So we have antinode at the top and node at the bottom. So the L is the length of the air column and V is the velocity of sound in air. So we have first the fundamental mode. So here you can see that the length of the air column covers 1/4 of the wavelength of the waves. So therefore lambda 1 is equal to 4L, or if you use V, the frequency F1 will be V by 4L. This is called the fundamental frequency, and it is also called the first harmonic. Now coming to the second mode, which is called the first overtone or the third harmonic. The length of the air column covers 3/4 of the wavelength. This is 1/2 and this is a quarter wavelength. So the total is L is equal to 3/4 of lambda 2, or lambda 2 is equal to 4/3 L, or using the velocity again we get the frequency F2 is equal to 3V by 4L, which is actually 3 times the fundamental frequency, and that is why it is called the third harmonic. And similarly we have the second overtone where the frequency is 5V by 4L, which is 5 times the fundamental frequency, so therefore this corresponds to the fifth harmonic. Similarly third overtone, which has a frequency of 7 times the fundamental frequency, so this is the seventh harmonic, and so on. So for example, the first harmonic, we have the fundamental frequency V by 4L. So if we measure the length of the resonance column corresponding to this particular frequency, then we can actually invert this relation to calculate the velocity of sound in air. In fact, this is a familiar laboratory experiment to find out the velocity of sound in air. This is the standing wave patterns in a resonance column which is open at both ends. So once again you see the various modes, the fundamental, the first overtone, second overtone, third overtone, and so on. So in the fundamental mode we have the length covering the entire wavelength of the waves. The first overtone covers the 2 wavelengths, the third overtone covers 3 wavelengths, etc. So you can see that the frequencies corresponding to these various modes are F1 is equal to V by 2L, F2 is equal to V by L, F3 is equal to 3V by 2L, F4 is equal to 2V by L, and so on. So you can see that the overtone frequencies are integral multiples of the fundamental frequency. In fact, here all harmonics are present, odd and even. Whereas in the case of the resonance column, which was closed at one end, the odd harmonics were absent.
The conch or shankh in Malayalam is a very good example for resonance. This is a naturally occurring source of sound utilizing the vibrations of the air inside. It can also be used as a musical instrument and has a spiral air column inside. The tip is removed and then the player blows air into the shell through the hole. The conch comes in different shapes and sizes. The frequency of the sound generated depends on the length of the spiral air column. The instrument, of course, functions as a resonance column closed at one end. Hence, the sound generated has only the even harmonics. Traditionally, the conch is considered as a divine musical device by Hindus. It is used at the time of the main aratis and pujas in Hindu temples. The blowing of the conch usually marks the beginning of an auspicious occasion. The conch shell is generally used at the beginning of the worship. Given the sound quality, it captures the attention of the devotees and helps in focusing in the mind of the people to the particular worship. In the olden days, the conch was used as a war bugle and it has also been used as a trumpet occasionally. Another important vibrating system, which is very important from the point of view of many musical instruments, is the so-called touch string. We have a certain length L of a string made of some material fixed between 2 points, and one end is run over a pulley and the weight is attached to that end, and of course the other far end is fixed to a peg. There can be a wooden base. So this length of the string acts as the touch string. The important quantities in this case are the tension T, which is decided by the weight suspended here, and the mass per unit length of the wire. The wave equation for sound waves in the string is given by dou square y by dou x square is equal to mu by t dou square y by dou t square, where x is the coordinate in the horizontal direction and y is the displacement along the vertical direction. The speed of the waves along the string will be given by v square is equal to t by mu. The wavelength and therefore the frequency of the waves will be specified by the boundary conditions and depend on the length of the stretched string L. For example, for a string fixed at both ends, the frequencies are Fn is equal to n into V by 2L. So n is equal to 1 corresponds to the fundamental, and n is equal to 2, 3, etc. correspond to the overtones, which in this case happen to be harmonics. These are the different modes of vibration of a string which is fixed at both ends. The fundamental, there is one antinode in the middle and 2 nodes at the 2 ends. Then the first harmonic is this one, n is equal to 2, which has twice the frequency as the fundamental, and there are 2 antinodes and 3 nodes, and so on. So therefore here all the overtones are present. The even as well as the odd harmonics are present. This is a homemade string apparatus. Here we have the weight at one end and the other end of the string is fixed. The string can be set into vibrations by one of several methods. The first one is by plucking. So one can hold the string at some point and pull it up by some distance. This is the direction of pulling, and then release it. So then the string will go back and start vibrations with respect to the original mean position. The second method of exciting vibrations in the stretched string is by means of what is known as a bow. The process is called bowing. The bow is made of a suitable material, and it will be drawn back and forth touching the string, and the friction between the bow and the string will actually excite vibrations in the string. The third method of exciting vibrations in the string is by striking on the string at some point. There is a striker for this purpose. So the string is struck by the striker at any of the intermediate points, and this force sets the string into vibrations. There is yet another process for exciting vibrations in a stretched string, that is by using a tuning fork. A tuning fork of a suitable frequency is excited, and it is kept with its base at some point on the base. Now the vibrations of the tuning fork will be passed on to the string, maybe via the wooden box, through the point at which it is tied, and that will be passed on to the string, and then the string will start vibrating. Irrespective of the method of excitation of the vibrations in the string, a disturbance is generated in the string in the form of displacement of the points in the string. These now travel along the length of the string and get reflected at the two ends. The two sets of waves superpose each other as per the superposition principle. Under suitable conditions, standing waves will be produced. Any general periodic disturbance can be represented as a Fourier series. Fx is equal to a0 by 2 plus summation over n is equal to 1 to infinity an cos 2 pi nx by t plus summation over n is equal to 1 to infinity bn sin 2 pi nx by t, where this is the DC part of the disturbance, this is the even part, this is the odd part, and t is the period of these signals. If we designate by omega 0 the quantity 2 pi by t, then fx can be written as a0 by 2 plus summation over n is equal to 1 to infinity an cos n omega 0 x plus summation over n is equal to 1 to infinity bn sin n omega 0 x. Here omega 0 is the fundamental frequency and n omega 0 are the harmonics. X is of course the displacement along the traveling direction. Therefore, the higher frequency components are actually harmonics. There are many musical instruments using a stretched string. Usually it will be made of a metal as the vibrating element. So a very common instrument is of course the piano, where the method of excitation of the vibrations is striking. Next we have the violin, which is also known as fiddle commonly in India. This is actually a bowed instrument. We have the bow by means of which the violin will be played. Next is the veena, which is again of prevalence in India. This is also a plucked instrument. Then comes the guitar, which is again played by plucking. The tanpura, again played by means of plucking. This is basically used as a shruti box. Then mandolin, again a plucked instrument. The santur, which is a struck musical instrument. The sitar, again a plucking variety. And finally we have sarangi, which is a bowed musical instrument. There are plenty of other types of musical instruments which are prevalent in various parts of the world. An important class of musical instruments called percussion instruments use a stretched membrane as a vibrating element. These provide the underlying rhythm, harmony and pulse for the main part of any musical event, providing a rhythmic and harmonic reference and beat. A two-dimensional elastic membrane under tension can support transverse vibrations. The membrane is held under tension by attaching to a rigid frame. Now this is a homemade percussion instrument. Here the membrane is stretched across the mouth of this plastic vessel, and it is supported by means of this rubber band, and it is played either by striking with a stick or with the hand or the fingers. The wave equation describing the vibrations in a stretched membrane is given by dou square u by dou x square plus dou square u by dou y square is equal to 1 by v square dou square u by dou t square. Here the u is the transverse displacement of any particle in the medium at the position xy, and the v is the velocity of the waves. The speed of the waves in a membrane depends on the in-plane tension, which provides the restoring force for the vibrations, and the surface mass density, which provides the inertia. In the same way that the speed of transverse waves on a string depends on the tension and the linear mass density. Invariably, the membranes used in musical instruments are circular in shape. But they can be used also in other geometries like the rectangular geometry. The various modes of vibration in the membrane depend on the roots of the Bessel function and are designated via two integers m and n. In the case of these membranes, the overtones are no longer harmonics. The four lowest vibrational modes for a circular membrane can be derived from the mathematical equations, and they look something similar to these diagrams. This is mode 0, 1. That means the 0 and 1 correspond to the m and n integers, which I referred to in the previous slide. So therefore, this is a sort of mode in which the particles vibrate. The membrane vibrates up and down like this. This is mode 0, 2. Of course, you can see the shape at a particular instant of time. So this will go down and this trough will come up alternatively. This is for mode 1, 1. There is something like here there is an antinode, here there is a node minimum, and so on. So this is for mode 2, 1. And you can see that this is the lowest frequency mode F1, and the other frequencies are 2.30 F1, 1.59 times F1, 2.14 times F1, etc. So they are not, the overtones are no longer harmonics of the fundamental. If they are harmonics, we should have got F1, 2F1, 3F1, 4F1, like that. Now we will just list some of the examples of common musical instruments using a vibrating membrane in it. So first of all, we have the drum. An example is something like this. So this is played by striking with the appropriate sticks. Next is the dholak, which is something like this, and it is played by striking the two membranes on either side with the hands. Now the drums of course have only membrane on one side. Then the damaru, which is famous as being held by Lord Shiva during his Tandava dance. So here also we have two membranes on either side, and one holds this with the fingers at the middle and then shakes back and forth. So in that process, these structures will hit the sides and thus make the sound. This is the coulumn, which is so famous in Indian classical musical concerts. So here we have an earthen pot. Of course, that will be specially made for this purpose, and it is played by playing with the fingers, striking with the fingers on the sides. Then idaka, which is usually played in temples for worship. This also has two membranes, one on either side, and it is played by striking with a suitable stick. The chenda, which is famous in Kerala temples. Here also we have two membranes and they are struck by sticks like this. So next is the tawil, which is also part of the temple festivals, especially in the Tamil Nadu area. So here also there are two membranes and this is struck on one side with a small stick and on the other side by means of the fingers. Then we have tabla, which is commonly used in Hindustani concerts in India. Here actually we have two pieces and they are also played by using the fingers. Then another percussion instrument which is commonly used in Carnatic music concerts in India is the mridangam. Again, two membranes. Then maddalam. And of course, something called a timpani drum, which has only one membrane. There are other varieties in the percussion type, and these use other materials as the vibrating element. For example, the cymbal, which uses a brass cups like this. So this is played by striking one piece against the other. Then the jalatarang, which uses porcelain or metal containers, and water is taken in these two different levels to cater to the different notes, and this is also struck with a stick. And there is also the bell, which is also made of metal, and there is a gong in the middle, so when it strikes the outer container, the bell sound will be produced. The xylophone, which uses wooden bars, and each wooden bar will correspond to a particular note of a particular frequency. This is also played by using these sticks. Then another common musical instrument which is played in Carnatic music concerts is the ganjra, which is, in English it is called a tambourine. Here also we have one membrane, but in addition this contains also pairs of small metal jingles on the sides. So when it is struck with the fingers, this also produces the metallic clanging sounds.
I will end the discussion on the physics of music at this point. This is Professor Muralidhara Varyar signing off from Murali's World of Physics with the promise that I will be back with yet another video on another aspect of physics. Till then, goodbye.